All right, so welcome everyone. So today we'll talk a bit about optical activity as it relates to enantiomers, right? And this is the unique property of molecules to chiral. We look at two enantiomers, like for instance, these two molecules shown here, okay? They are in fact mirror images that are not superimposable, right? So if we try to line up these two forms of 2-chlorobutane, right, two enantiomers of 2-chlorobutane, I can, for instance, line up the alkyl chain, the 4 carbons line up fine. But when I actually go to line up the chlorine groups, they actually don't line up properly, right? In that case, one of the chlorines in the one form points to the right, the other one points to the left, right? So these two are enantiomers, they're non-superimposable mirror images. So if we have these two forms of 2-chlorobutane, all of their other physical properties are exactly the same, right? So the melting points, boiling points, their solubility will all be exactly the same. The one feature that's a bit different is their interaction with plane polarized light. It's sort of a unique and kind of weird property of enantiomers. So as we go about thinking about how these molecules behave, okay, can go ahead and say, okay, so first of all, we have these two forms of 2-chlorobutane, okay? So we can go ahead and assign the stereochemistry of these. So for instance, there's the one form here, okay? If we use the Kahn-Ingold pre-log rules, let's say that we assign those priorities in green for this form, okay, this enantiomer. We have an implicit hydrogen here, which is not drawn in. But because we see the Cl is wedged and the other two groups are flat, we know that H, the implicit H, has to be back. Okay, so that's a dashed H there. So if we use the Kahn-Ingold pre-log rules for this, okay, first of all, based on atomic number. So in that case, Cl will be the highest priority. As always, hydrogen will be the lowest priority. Hydrogen has the lowest atomic number of all the elements out there. And it really leaves us with these two sides here to choose between. This side here is H, H, H coming off this carbon, right? So H, H, H versus C, H, H coming off this one. So C has a higher atomic number than hydrogen. So that makes this side here have priority 2, and this side have priority 3. Okay, so if we go ahead and try to assign the stereochemistry to this particular molecule, okay, we can use, say, our hand method that we have in our other YouTube video. So we can line up our hands with the low priority group being lined up with our thumb, right? So the low priority group in this case points into the screen, okay? And we can use the method where we line our finger up with the priority 1, which is chlorine, close our hand to 2, and then finish off closing our hand to 3. So 1 to 2 to 3 with our low priority group going into the screen. That works with our left hand, okay? That makes this one here the S enantiomer, okay? And then if we go ahead and do the other mirror image, okay, again, our priorities are 1 for the chlorine, 4 for the hydrogen, that's implicit, but it's actually a dashed group because all the other groups are drawn in. Again, our ethyl chain will be priority 2, and our methyl group will be priority 3. Okay, in that case, if we line our hands up with the low priority group going into the screen, so thumb going into the screen, okay, start at 1, close to 2, finish at 3, 1, 2, 3. Okay, that works with our right hand, so this is the R enantiomer. Okay, so that's fine. So we're just an example of assigning R and S stereoisomers. But if we want to talk about that unique property of chiral molecules, okay, or asymmetric molecules, we have this idea of enantiomers rotating the plane of light, right? So if we imagine here's our plane of light, plane polarized light in one direction, say in the horizontal, the R enantiomer would rotate it in one direction by a certain amount. The S enantiomer will rotate it the same amount, but in the opposite direction, right? So the light, instead of being horizontal, will be at some kind of angle after it passes through a sample which contains an excess of one or the other enantiomer. We can't predict whether R or S rotates left or right, but what we do know, if the S rotates in one direction, the R will rotate the other way. But in practice, a lot of the time, we have mixtures of the two enantiomers. We may not have 100% of one enantiomer and 0% of the other. So we define this concept called enantiomeric excess, or EE, right? So this EE is enantiomeric excess. And this is the difference between the percentage of the one enantiomer less the other. So let's say that we have a solution which is 90% R and it is 10% S, okay? In that case, the enantiomeric excess would be 90 minus 10. So that would actually be 80% EE, right? The enantiomeric excess would be 80%. Okay, so we first of all need to define this concept of enantiomeric excess before we can actually calculate rotations of mixtures of two stereoisomers. Okay, similarly, we might have a different mixture, which would be, say, 60% of the S enantiomer and 40% of the R. So in that case, the enantiomeric excess would be 60 minus 40, okay, which would be 20% EE, 20% enantiomeric excess, right? It's the amount excess of one enantiomer versus the other, okay? So we could always define an enantiomeric excess as either the positive number or negative number, but we always retain the one which is positive. We're essentially saying that there's the excess of the one which gives a positive number. So whichever is larger, whichever gives a positive number, that's the one we report. Okay, so we can now go ahead, assign stereochemistry. If we're given a mixture, we can define an enantiomeric excess. How does this relate to the observed rotation, how much that light rotates compared to what you would expect for 100% of the pure enantiomer? And the formula we're going to use is that the rotation observed for a mixture is the rotation we would expect for the pure enantiomer multiplied by its enantiomeric excess. The idea being, if the pure enantiomer rotates a certain amount, but if we have a mixture now of R and S, right? If the R is rotating clockwise and the S is rotating anti-clockwise in that case, if we have an excess of the R, but some of the S, we won't get the full rotation for the pure R enantiomer because some of the S in that system is rotating things the other way. So we don't get the full rotation, we only get a partial rotation because we have some S that's undoing what the excess of R is doing to us, okay? So that means we have the rotation of the mixture being the rotation of the pure one compared to the enantiomeric excess, right? Scaled by the enantiomeric excess. So let's go ahead and do some examples here. Okay, so this molecule that we assigned earlier, 2-chlorobutane, based on this reference down here, okay, so this reference here, reports that the R enantiomer is predicted to rotate just under 34 degrees in the negative direction. Okay, so R enantiomer rotates around 33.8 degrees negative. Okay, now that means the S enantiomer rotates plus 33.8 degrees in the pure enantiomer form. But what about if we have a mixture? Okay, so that tells us that the specific rotation for the R enantiomer is negative 33.8, What about though if we have some mixtures, okay? So one mixture is 66.7% S, and the remainder is R, so 33.3% R. And mixture B is the other way around, so it's 20% S and 80% R. Okay, so how do we calculate first the enantiomeric excess, and then second, the rotation we would observe in these mixtures, okay? So the enantiomeric excess, okay, of A, so we know that we have 66.7 of S, 33.3 of R. So the EE is 66.7 minus 33.3. Okay, if we calculate that difference, it is equal to 33.4% of the S enantiomer, right? S enantiomer in excess. Okay, so that's 33.4% with the S in excess. Okay, now what about B? So B, the enantiomer in excess is R, and we've got 80% of that, so it is 80 minus 20, okay, equal to 60% EE, 60% enantiomeric excess, but this time it's the R in excess. Okay. So let's now predict the rotations that we would observe for these samples, okay? We already know that the R enantiomer, right, that is the alpha pure, alpha R is negative 33.8. That tells us alpha S is plus 33.8. Okay, so in this first example, where the S is in excess, okay, we can go ahead and use 33.8, but the positive one of it, right? So 33.8 degrees as alpha pure. We know S is in excess, so we're going to get a positive rotation, the opposite of what we get for the R enantiomer, times by 33.4 divided by 100, right? So it's a third of 33.8 degrees. Okay, if we calculate that, we end up with a rotation of plus 11.2 degrees. I'm just rounded 11.2 to 11.3 degrees. Okay. Now, mixture B has the R enantiomer in excess, right? We know the R rotates negative, and so the alpha pure we need to reference to the R enantiomer, so we have negative 33.8. Okay. Times by, in this case, 60 on 100. Okay, 60 over 100. Okay, and if we do that calculation, okay, we end up with a negative 20.2 degrees. Okay, so what this is telling us is mixture A does rotate positive, okay, because we have the S enantiomer in excess, but doesn't rotate all the way that the S enantiomer would, which would be 33.8 degrees. Instead, it rotates 11.2 degrees, or about a third of that, because we have an enantiomeric excess of about a third. Mixture B, the R enantiomer is in excess, so we expect a negative rotation, negative direction of rotation. But again, because we have some S in there, okay, we don't rotate all the way that we would for a pure R enantiomer. Instead, we rotate 6/10, or about 60% of it, so 20 degrees. We have a 60% enantiomeric excess. Okay, so hopefully that's a useful video that kind of highlights how you can, assign stereochemistry, how you can calculate enantiomeric excess of mixtures, and how you can use this to predict the rotation of a sample which contains mixtures of R and S enantiomer based on that enantiomeric excess. Okay, thank you very much, everyone. Good, and all the best.